Today we're going to start with section 9.1, Determining Probabilities. And kind of like when we start with any new chapter, we have a little bit of vocab at the beginning just to make sure that when I say a word and you say a word, we mean the same thing. And it doesn't always, work that way, even between like math and English definitions of things. So we want to make sure we're on the same page. So the thing we're going to start with first is the word experiment. So this isn't necessarily like science experiment, right? Not Dr. McWilliams' class. But we're referring to an experiment means any activity whose results can be observed and recorded. Any activity. Like I could tell you, we're going to do an experiment today. We're going to see when I pick my son up and I tell him that we have to go to the grocery store after school, what's his reaction? I can tell you he's going to be mad, hot as a hornet, every single time, right? But that's an experiment, right? It's not a science experiment, it's a social experiment, but it's an experiment. Outcome. An outcome is the possible results of the experiment. He could be fine. He could be grumpy. He could ignore me. Those are the outcomes, right? He could do other things too, potentially, but any outcome, any result is an outcome. The sample space is the set of all possible outcomes. So it's like if I took all the collection of things that could happen as a result, that would be the sample space. And an event is any subset of the sample space. So, let's talk about a dice, because a dice works really nicely for this description. So if I were talking about an experiment, the experiment could be I'm going to roll a single die. Fair, six-sided die, the normal ones you see in all the games, okay? An outcome is any number that shows up when I roll the die. It's a 3, it's a 6, it's a 2. Can't be a 7, right? So there's some things that are outcomes, there's some that are not. The sample space. The sample space would be simply a listing of all of the options. 1, 2, 3, 4, 5, 6, and we put it inside of those funny curly braces that you've seen used before, okay? So it's a listing method, like the roster method for those of you who've had number theory. An event is any subset of the sample space. So it could just be the event is I'm rolling a 3. But the event also could be I'm rolling an even. Okay, or maybe the die is colored and the event is I'm rolling one of the sides that's yellow. All right, so it doesn't necessarily have to be just a single item. It could be a description that several of the outcomes satisfy, like even. All right, Theorem 9.1 talks about the law of large numbers. Bernoulli is the mathematician's name who's credited with this theorem. It's called Bernoulli's theorem. Bernoulli's theorem says if an experiment is repeated a large number of times, the probability approaches a fixed number. So imagine flipping a coin, and you flip the coin, and you flip the coin. If I flip the coin 1,000 times, it's a large number, I would expect that I'm probably going to get 500 heads, 500 tails. Okay? That's the law of large numbers. Probability is when you're doing let me write this in here, theoretical. Theoretical probability is the number of ways you can get a certain event to happen compared to the number of items in the sample space. For example, when I said earlier, if I'm having a baby and it's either a boy or a girl, it's a 50-50 probability, right? What did I mean by that? I mean, like, I've only had one child, who's with me now, right? I only have one child, and she's a girl. So I can't say, well, I've had Bernoulli's law of large numbers, and I've had infinitely many children, and half of them are boys and half of them are girls. It doesn't work like that. It's a theoretical probability. What I'm doing is I'm saying there's two outcomes in the sample space, right? The N of S on the bottom is number in the sample space. Boy, girl, two options. And if I'm wanting to know what's the probability of having a girl, it's one of my two choices. So that's what this is describing, the number of ways of getting whatever desired outcome or, the outcome you're considering compared to the number of ways of getting any possible outcome. If I'm rolling my die and I want to know the probability of getting a number that's bigger than 5, number that's 5 or bigger, let me say it that way, number that's 5 or bigger. Well, there's two outcomes that are 5 or bigger. I can get a 5 or a 6. So there's 2 on the top. And there's 6 possible, completely possible outcomes that would go on the bottom. So I have a 2 out of 6, or you could divide it and you get 1/3 probability of getting a number that's a 5 or larger on my die. Mutually exclusive events are events which have no elements in common, like rolling even and rolling odd. Both cannot happen at the same time. Okay? So mutually exclusive events have to be talking about the same experiment for them to make sense. I can't say rolling an even and having a girl. They don't even make any sense to talk about like that. They're nothing to do with each other. So write down, because this is a really common confusion for people, is this mutually exclusive events. Because we're going to encounter another word a little bit later, or a phrase, that sounds similar but does not mean the same thing at all. This has to be within the same experiment for it to make sense. Rolling an even, rolling an odd. Rolling a prime, rolling something that's a composite or not a prime. We'll say not a prime. Okay? So something that is mutually exclusive. Rolling a 2 and rolling a 6. It doesn't even have to cover all possible answers. It just can't happen at the same time. I can't roll a 2 and a 6 if I'm only rolling the die one time. Okay? So those are mutually exclusive events. I feel like all I'm doing is talking. I'm so sorry. We're going to get to some examples soon, I promise. All right, Theorem 9.2. Theorem 9.2 says that if you have any event and you have the sample space S, then the probability of the event is between 0 and 1. So this really is the equivalent of saying 0% to 100%. Every probability is between 0 and 1. It's not 110% chance it's going to rain today. We say that, but we know that that's not really what we mean, right? We're using our English to make sort of we call it a hyperbole, right? We're making an extravagant or an exaggerated statement. But all of our probabilities really are between 0 and 1. They're the decimal representation of percentages. So it's between 0% and 100%. That's what we're looking at. The probability of an event is equal to the sum of the probabilities of the disjoint outcomes that make up the event. So let me show you what that means. My example says to consider rolling a 6-sided die. If I want the probability of rolling an even, which we've already said would be 3 evens. Actually, we didn't say it, but we did it. We did one similar. 3 evens out of 6 total, right? That's the probability of rolling an even. Well, I could separate these into disjoint or mutually exclusive. That's the same word, mutually exclusive and disjoint probabilities. I could instead find the probability of rolling a 2, the probability of rolling a 4, the probability of rolling a 6, and add those distinctly different probabilities together because they are disjoint or mutually exclusive. So this is 1/6, 1/6, and 1/6. And of course, these are equal. So that's what 9.3 says, is that I could just break it apart into something simpler to find. Okay, even and odd's not a very difficult concept, but maybe there's a way to break something apart, and it does make it simpler if you can break it into smaller pieces and look at those pieces individually. All right, one more piece of information about mutually exclusive events. If the events are mutually exclusive, like the last problem, rolling a 2, rolling a 4, rolling a 6, they're mutually exclusive, then the probability of the 2 events happening, either or events happening, is simply the sum of the 2 probabilities. So I know not all of you have had number theory. Those of you who have should recognize that symbol. Does anybody want to remind us what that symbol actually means? It means or. That's the or symbol. Yeah, we'll use the other one in a minute here for and. That's or. So this is the equivalent of saying, I'm going to use my example from before, the probability of rolling a 2 or a 4. Well, I can't do both at the same time, so I could just find the probability of rolling a 2 and add it to the probability of rolling a 4. That would be an example of this. Now, it doesn't work for everything, right? Because not all events are mutually exclusive. For example, even and odd, mutually exclusive. Even and prime, not mutually exclusive. Okay, 2 is both an even number and it's a prime number. And since it's counted in both sets, I would not be able to separate it like this, because even numbers and prime numbers are not mutually exclusive. Now, if we do have an event A, and again, this is another number theory symbol. This is A with a bar on the top of it. Can somebody remind us what that bar means if you've had number theory? The opposite of, there's another word we use sometimes too. Complement. What it means sort of in a long form is it means not in A. I've got A and I've got not A. Okay? So evens and odds are a really good example. I've got even and I've got not even. I mean, we call it odd, but not even is pretty much the description, right? It's even and it's not even. But what it's telling you is that if you have those two possibilities where you can take in A, not in A, and you add the two probabilities together, you get the whole sample space, right? I either win $1 million in the lottery or I don't. 100% chance that one of the two things is going to happen. I'm not going to because I don't play the lottery, just in case you're wondering. But, right? 100% chance one of those two things is going to happen. So what you see right here are 3 different equations that are really just all the same. They're just manipulated, add and subtract each side of things. So the first one's the one that I already mentioned. The probability of the event plus the probability of the event not happening is equal to 1, right? Winning lottery, not winning the lottery equals 1. I could also say, what's the probability of winning the lottery A? Well, it's 1 minus the probability I don't. Just subtract it to the other side. And likewise for the third one here. Okay, one more set of definition things, and then we're going to do a problem. This is actually just a mushed together table, kind of, a listing of all the probability theorems, most of which we've already talked about. I haven't actually defined the first two, and there's a symbol that's showing up that you may or may not be familiar with. Apparently this is the day to talk about number theory. Does anybody remember from number theory what that symbol is? Null set or empty set. Yeah, so this is the probability of the null set or the empty set. That would be 0, right? The probability that you're going to go to my house today and there's going to be a baby crying is 0 because I don't have a baby. The probability you go to Danielle's house and hear a baby crying is probably not 0 because she has a baby, right? So it's an impossible event when there's a probability of the null space or the null set. Probability of S, the second one, S is the sample space. It means anything in the realm of possible happening. Well, the probability that something in the realm of possible happening is 100%. It's 1. It's a certain event. Certain event. And then everything else is between 0 and 1. Okay, 0 is the impossible event, 1 is the certain event, and anything in between is somewhere between a probability of 0 and 1. Right? So like the weather people can't tell you that there's a 110% chance of raining, but neither can they tell you that there's a negative 10% chance of raining. Right? It doesn't work like that. It's always between 0 and 100% or between 0 and 1. All right, there's the symbol that I mentioned was going to come up. See the upside down U? That's intersection, for those of you who were guessing that from earlier. I think that was actually an earlier definition, and I probably failed to mention it there. I'm so sorry. This says if A intersect B is the empty set, it just means that they're disjoint or they have nothing in common. Okay, so write that down. This means that these are mutually exclusive, or you can say disjoint. Okay, so if their intersection is the null set or is the empty set, means they have nothing in common. Then when we look at the probability of the union, we can separate it into 2 different pieces. It's probability of A plus the probability of B. Okay, but they have to have nothing in common first. This next one we haven't talked about yet. This one's brand new on this slide. We actually see a version of this happening in number theory when we do Venn diagrams. So if you're like, that sort of feels familiar, that's probably where you're going to remember it from. Or if you've had contemporary math, maybe online, contemporary math, we do it there as well. This one's talking about what happens when we have any sets A and B. They don't have to be disjoint. So let me go back to my example where I talked about prime numbers and even numbers, okay? Because they're not disjoint. Are you with me? Prime numbers, even numbers. So if I were to talk about the prime numbers, we're just doing our six-sided die for the moment, okay? So if I were to do my prime numbers and I were to do my six-sided die, hang on. How many prime numbers are there between 1 and 6? There are 3 of them. What are they? 2, 3, and 5. 2, 3, and 5 are the prime numbers. 1's not prime. If you're concerned about that, I promise, take number theory. We'll clear that concern up later, but we're not doing that today. So just trust me, 1's not prime. 2, 3, and 5 are 3 prime numbers. So the probability that it's a prime number plus the probability that it's not we'll do even number, minus the probability that it is prime and even. That's what this would say with my example. So you guys just told me that there are 3 prime numbers out of 6 on a die. How many even numbers are there? 3. Different 3, but 2, 4, and 6, excuse me, so there's 3 of them. And how many numbers are both prime and even? Just one. Which one is it, Ariel? 2. The number 2 is both prime and even. So there's 1 number out of 6 numbers that we have to subtract. 3 plus 3 minus 1 gives me 5 out of 6. Now let's just go back and count. Is the number 1 prime or even? Nope. Is the number 2 prime or even? Yep, it's both. Is the number 3 prime or even? Yep, it's both. Is the number 4 prime or even? Yep. How about 5? Yep. And 6? Yes. So I listed all the numbers. There was only one of them that failed to work. It was the number 1. So there are 5 ways that the number is either prime or even by rolling the standard 6-sided die out of 6. That's the 5 out of 6 at the end. Now what's really happening here? Well, compare the 2 formulas here. One of them has the, wow, that's not what I wanted. One of them right here, and then the other one that's highlighted in blue below. What's the difference in the 2 formulas? What does the blue one have? Yeah, it has that second part, right? It has this piece at the end. It has the part where things overlap. Well, I don't have that in the one that I circled in red because they don't overlap. That's the difference. It's the only difference in the formulas is that when they don't overlap, I don't have to worry about subtracting things. And the reason I have to subtract them is because when things overlap, they get counted twice. So when I went through all the even numbers, I counted 2, and when I went through all the prime numbers, I counted 2. 2 got counted twice. All right, last one on this slide before we can do some real problems. The probability of A complement is equal to 1 minus the probability of A, and we already wrote that one down earlier as well. Are you ready to do an example? All right. Every time I do this example, I have to talk a little bit about deck of cards because our familiarity might not be the same for everybody in the room. So if you're not so super familiar with a deck of cards, jot some of the things down that I'm going to tell you. So in a standard set of cards, there's 52 cards. Half are red, half are black. So 26 red, 26 black. There are 4 suits. The 4 suits are clubs, spades, both black, diamonds, and hearts, both red. There are 13 of every suit. So there's 13 spades, 13 clubs, 13 hearts, and 13 diamonds. Another way to break the cards up is in terms of their value, the face value of the card. The smallest numerical card is the number 2. The largest numerical card is the number 10. So you've got number cards that go from 2 to 10. You also have Jack, Queen, King, and Ace. I'm pretty sure that nothing that we do actually asks you about high cards versus low cards. Sometimes it'll ask you about face cards. The face cards are the Jacks, Queens, and Kings. Ace is not considered a face card. Sometimes it'll ask you about number cards. The number cards are just the 2 through 10s. Those kinds of phrases. I think that's probably enough for what we're going to encounter. If that's not the case, we'll deal with it when we come across it again. This problem wants us to find the probability of certain things happening. So, for example, on part A, and then it asks about equal, not equal. We'll do that in a second. But it asks for face cards and not a face card. So it's actually enough to consider one suit. I'll prove that to you in a second. But if you think about the face cards, which cards did I say were face cards? Jack, Queen, King. How many of them were there? 3. And within a given suit, there are 13 cards. So the face cards are actually 3 out of 13. If you want to actually count them, you're going to get Jack of clubs, Jack of diamonds, Jack of spades, Jack of hearts. Queen of clubs, Queen of diamonds, Queen of spades, Queen of hearts. King of clubs, King of spades, King of diamonds, King of hearts. There's 12 of them. You'd get 12 if you counted everything out. You get 12. 12 out of a total of 52 cards. So you can do this as 3 out of 13. That's fine. Or you can do it as 12 out of 52. That's fine. If you were to reduce the 12 out of 52, it would reduce to 3 out of the 13. Can't speak today, but 3 out of 13. Okay, so either of these versions for your face card are fine because they're actually equal. So I'm just going to put this in, I don't know. How about a blue circle like that? They're equal to each other. Either one you want to use. Now we're going to do the same thing on the not a face card. So if there are 3 cards out of the 13 that are face cards, how many are not face cards? How many? 10. 10 are not face cards. So 10 out of the 13 are not. Or you could count them all up, right? You know, you could go through and you can count. You got 2, 3, 4, 5, 6, 7, 8. You can count 10 of them. 10 times 4 suits would be 40, all that jazz, okay? So you can do it that way if you want to. You'll end up with 40 out of 52 cards instead of 10 out of 13. Okay, so either that or you're going to have 40 out of 52. So I don't care if you want to compare the ones that I've circled in blue to one another or the ones that I didn't circle in blue to one another. But what they're asking you in this question is, does this number equal this number? No, it does not. These are not equally likely. So yes, there are 2 outcomes. I could draw a face card. I could not draw a face card. It doesn't mean it's a 50-50 shot. Just because there's 2 outcomes, there's so many more cards that aren't face cards that I'm still far more likely to draw those than to draw the ones that are. How about clubs, diamonds, hearts, and spades? Well, again, you can count if you want to. How many clubs are there? There are 13 out of 52. How many diamonds are there? 13 out of 52. Hearts are 13 out of 52, and spades are 13 out of 52. So you could do that. Or if you want, you could write down 1/4, 1/4, 1/4, 1/4, because that's what they reduce to. Right? They do. Either way's fine, I don't care. Are these equally likely? Yep. These are equally likely. How about black versus red? Yeah, it's 26 out of 52, or it's 1/2 and 1/2. Either way. Are these equally likely? Yes, they are. Equally likely. Okay, the last one in this section. King, queen, ace, even and odd. Okay, let's do these out of 52 cards just because it's, I think, maybe easier to count them that way. So how many kings are there? Not 12. That's how many face cards we had. What was it? 4. There's 4. 1 king of each suit. How many queens are there?
4.
How many jacks are there?
4.
4. All out of 52. How many aces are there? 4. How many evens are there? Yeah, not 4, right? How many evens are there? Did you count them? I didn't count. 2, 4, 6, 8, 10, 12, no, 10. So there's 5 times my 4, so 20, yep. And how many odds are there? 16. There's actually 1 fewer per suit, so yeah, there's 16. So are these, oh, and you could reduce them if you want to. By all means, go reduce if you want, but you don't have to for the question to be complete. It asks, are these equally likely? That almost worked till we got to those silly evens and odds at the end, right? Yeah, so these are not equally likely. All right. Are we done with cards? Want to do something different? All right, let's do something that's not cards. All right, so this, again, feels a little bit like when we did Venn diagrams and number theory, where we got these paragraphs that sort of describe things. So it may be more helpful to rewrite them and organize them in a different way if that's helpful to you or not. This one's not too bad. Some on your homeworks might be a little bit different, but let's read through it together. A civ class is composed of 21 men and 34 women. There are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, and 3 math majors. The next statement's really important. It says, assuming no one has a double major. Because if they do, all of our numbers are going to be kind of, questionable, right? Because what if somebody is a math major and an ed major? What do I do with that, right? So it says, assuming no one has a double major. If a single student is chosen at random, what is the probability that the student is the following? So the first one says female. So how many females did it say there were? It's 34, right? So it's 34 out of how many? Okay, where'd you get 55, Samantha?
I added the 21 men plus 34 women.
Wonderful. So the 21 men and the 34 women added together give me 55. So I have 34 out of 55. If this reduced, we would reduce it. It doesn't, so we're going to leave it the same. If fractions really bother you, you can turn them into decimals, but not if the decimals are repeating. Okay? I know 7.3 was super fun and exciting, and everybody loved the repeating decimals, but we're not going to write our answers as a repeating decimal, okay? So if it terminates and you want to use decimals, go for it, but otherwise fractions are great. How about science majors? What probability is it that we choose a science major? 12 out of 55. Okay, there's 55 students total, whether I divide them up by gender or whether I divide them up by major. There's 55. And there's 12 of them that are science majors. How about an English major or a religion major? 18. So where did the 18 come from?
It was the 5 English majors and the 13 because of the 4.
There it is. Cool. So again, that's why I needed to know that there's no double majors, right? Or I wouldn't be able to do that. These are mutually exclusive categories. How about the one that says neither a math major nor a science major?
Is it 40 out of 55?
Yes, it is. So how did you do that?
I took the science major plus the math major and then subtracted it from 55.
Oh, wonderful. Okay, so there's 55 total. And you took off the science, so minus my science folks and minus my math folks. And that is one way to do the problem. Did anybody else think of doing it differently?
I should just add up all the other.
You could. You could add up the other ones, especially if there's fewer or more of them in one direction or the other. Absolutely. So I could, instead of doing that, I could have added up my 22 ed majors, my 5 English majors, and my 13 religion majors, and I would have still gotten the same 40 out of 55. This 40 out of 55, it reduces, so let's actually do that one because that's the only one I think that did reduce. What will they divide by? Hang on, sorry, let me shift this over, I'm out of space. I divide by 5 and I get 8 out of 11. Yeah, that's right. Okay, any questions on that one? All right. A couple more examples. Example number 3. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then, according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What's your reply?
Has to be a great large number, right?
Okay, so we've got one issue is that what we're talking about applies to large numbers. And inherent in what we just described is that we believe that the numbers that we're getting given are not large enough to count. There's also another problem with what his or her reasoning is. Okay, so the law of large numbers doesn't apply to an individual instance of something happening, right? It applies to the grand scope of all the things that happen over a period of time. So the other issue is that the law applies to all outcomes in a sample space. Not one specific outcome. Yeah, so you're right. It's still one heads. I don't care how many children that you have that are girls. If you get pregnant for the 17th time and you've had 16 girls, you're still 50-50 shot on that being a girl. Just the way it works, right? I would actually say that 16 is probably a large number in that scenario, wouldn't you? Probably is. Yeah, still not what it's applying to. All right, I have another example here. This one's an interesting one. This is a spinner. The following spinner is spun 100 times. All right, the spinner is the little red dial piece that you can see. It's not super clear, but it's the red piece. Joe claims that the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture, and what is the probability that the 4 will occur on any spin?
It's like the same amount of space that the spinner will hit because it looks like it's at like a right angle. So
Okay.
it's like the same amount.
Okay, so the issue is that Joe is not considering the size of the angle. A spinner spins through an angle. It doesn't really care about what area of the region it is. It cares about the angle in the region. The angles here are all 90 degrees, or you could say they're all the same, right? So the probability of spinning a 4 is actually what here? It's 1/4. Now consider this alteration. What if this weren't a spinner? and it were a dartboard, would that matter? Yeah, Brittany's over there shaking her head pretty good. Why would it matter, Brittany?
Because then you're using the whole circle, not just the corners of it.
Yeah, then the angle doesn't matter, right? The game changes significantly. We got a pointy thing involved now, right? Yeah, the game changes significantly. Now it matters that the area is actually bigger in one space than it is in another. So, if this were a dartboard instead, would Joe's conjecture be correct? Yeah, Joe would be right here. And like we said, it's because the area would be the target. I don't want to say to target. The area would be the space for the target. I don't know if that's any better. Rather than the angle measure. Any questions on that? Michaela?
How would you find the probability of it?
Yeah, so if you really wanted to do that on this one, you'd have to know a lot more specific information about where this is being divvied up. You wouldn't be able to with the given information here. You could definitely say it's more than 25%. I think you could go with that. Probably visually you might be inclined to think that it's more than half, but you would not be able to actually even prove that part of it. Any questions on this? Yes, of course. Okay, so I've still got the thing rolling because Lily's not here and I want to make sure she hears this just like you guys do. So I will not be here on Friday because I'm visiting Jackie Stone out in Edmond for her student teaching. And the next lesson is actually one that I really, really want to be able to do in person and not do it on a video. So here's what we're going to do. This section is finished. It's over. It's done with whatever. I'll be on campus earlier than that during the day, too, for you to bring redos by, so that's not a problem. So any redos can still come in and out on Friday. But if you have questions on this, I'll be around on Friday morning. All that's good to go or whatever. It won't be due till Monday. Okay, so this homework and group work are all now officially assigned. They'll be due on Monday, all right? And we will simply shift our 9.3 into or 9.2, into Monday, and 9.3 will shift, and we'll find space later. I'm pretty sure that that'll be okay. But I want to do 9.2 in person. Also, just in case the class before you hears that I'm gone, their class is still happening, at least the majority of it. So don't go telling them that they don't have class, because they do. You just don't. Okay? Everybody good? Awesome.